Hello, this is Mr. Jackson, and today I want to talk about friction. Friction is not a hard idea, but it has some tricky places in it. So I just want to make sure I explain this to you. You'll understand. Just follow along, okay? Here we go. Friction, in its basic definition, is a resistance to motion created by two surfaces interacting. So when two surfaces rub together, they create friction, or they slow objects down. And we've been adding this to our diagrams. And there are two ways to actually increase or change friction. You could decrease it too, but these are the ways, if you think about friction, this will help you understand the formula I'm going to develop, okay? So one way to change friction is to change the surfaces you're working with. So here I go. I have two surfaces. I have this box. These two boxes are identical, but one is sitting on a smoother surface and one on a rougher surface. So we'll put the idea that this is smooth and this is rough. Well, what's happening is, as these surfaces are different, there's more different kinds of contact. Here, the object slides easily over the surface, but here it hits too many of the points, and so it causes more of the surface to slow it down. So when you change the surface, you change how much friction you encounter. And so we call that roughness mu. And that's a Greek symbol, okay? And I just think of it as a U with an extra long tail in the front. So there is a roughness rating, and we'll talk about that here in a second. But I'm going to show you a real live example. The next way to change friction is to change the forces on how much the surfaces are together. Are they actually together more? Or are they harder? So an example, look, my fingers have friction. And so if I rub them, I can feel the friction creating heat. And so there's a roughness to my hands. But if I push harder together, so my hands, I'm pushing harder, and then I rub, I can feel the heat even more. That means I'm pushing the surface together harder. Well, if you can push surfaces together harder, then you can get more friction. Think about if you've ever worked with sandpaper. Sandpaper, you can push on a surface, but if I push harder, I can get more friction. So how much the surfaces push together is important. And you can change that by changing the weight. So you know, if you push down with an object because its weight will push down, then the surface pushes back with so much equal force normal. But if I put a heavier object on the same surface, that heavier object has more weight, and that greater weight has more resistance from the surface. It pushes back up. So then what happens is, now you have more friction because you have more weight. So when you change the weight, you actually change how much those two surfaces interact, and you can get more friction. Or you can push harder. Okay, so I could take this surface and push down harder, and if I push down harder and it doesn't go through the table, then the table pushes back more. So you could actually just add on a push if you wanted to. So that gives us our formula for friction. Our formula for friction is defined as mu Fn. That means these two must be multiplied together. So I can get more friction if I have a rougher surface. So if I was going to give you a rating, let's say this is a smooth surface, this surface could have a mu of roughly, let's say, 0.2. Okay, but then this surface could be rougher and it slows your objects down more, and so this may have like a mu of 0.6. That's just an example. And so as mu gets bigger, that means you have a rougher surface. Okay, and so as also, if you have a bigger weight, you have more force pushing back on the table, and you grind the surfaces together more. So if Fn, the support force, gets bigger, that also gives you more friction. Okay, so these are the two ways that friction can be increased as well as decreased if I want to lighten it, okay, or smooth the surface. So this is the general equation for friction, and we're going to use that in this unit. So I want to do this for you really quick, because there's going to be talking about right now is I'm talking about two types of friction, and this is where it can get a little confusing, but it's not a big deal. Okay, there is what's called static friction or starting friction, and then there's kinetic friction, which is called moving friction. once the objects are actually in motion, they begin to move easier. So what is starting friction? When you first encounter an object sitting on another object, you have to push hard because in general, more of these little grooves have been filled with the other surface, and so they've got to be pushed out of those holes. But once you're moving, okay, and you have your rough surfaces, and once you're in motion, you only contact the tops of the friction or of the surface, and so you can move across it easier. So let me give you an actual physical demonstration. I have here a board that has all kinds of surfaces on it. So here I've got cardboard, I've got cork board, I've actually got real sandpaper. You can see where it's been taking off the wood of this, and then I've got like a laminate. And they all, I can feel them, they all feel different. And so in a sense, if I was going to think about it, they all have a different mu because they're all rougher in different ways. So this one's smooth, so it has a low number. Sandpaper is very coarse, it has a higher number. The cork board, okay, actually feels rough, but you'll be surprised it actually has less friction than the laminate because it has these points that are smooth on top and allows things to slide across easier. And then I have the cardboard here, and that has a little bit more pull and stop than the cork board. So I'm just giving you a rough rating for them, okay? These are my numbers, they're not actually real, but it just gives you an idea of roughness. So I want to show you a starting friction versus kinetic friction. I want to show you this. As I'm pulling this, you'll notice that I have a little scale here on my spring, and my scale has a Newton measurement. See, 0.25, 0.5, 0.75, 1 Newton. And so this spring and this little line, when you pull harder, it tells me how much I'm pulling against the spring. And so if I hook this up here and I move this across, you notice that, and I've got to move it back here a little bit so I can get it out here. To get it started, okay, I'm pulling and the block is not moving. So that is the static friction. You can pull, but if you don't pull hard enough, the block will not begin to move. But once I begin to move, you notice that the spring jumped up. So let me do it this route so you can see it better. Okay, so here I have my block. I'm pulling on it, and I'm trying to get this block to move. But as you notice, it won't move until I get a certain amount. So that friction is called static friction. But once I begin to get it to move, see, I've got up to 175.2. You see how it jumped back up? Because to move it, now all the little surface imperfections are just bouncing off the top of the sandpaper, so there's less interaction. So when it's moving, there's actually less friction once I get going. It's kind of like if you've ever pushed a car, and I've had to do that before. You push really hard at first, but then once it begins to roll, the car isn't as hard to push because now all the parts inside are moving instead of just sitting still on top of each other. So static friction is when it's trying not to move and it's just trying to start moving. It is much higher than moving friction. So now I'm at 1.5, but watch, as it goes, and I keep going higher and higher, but then once it starts moving, it jumps up. It jumps and it goes lower. So you have static friction, and you see how it jumped up? Then it goes to kinetic friction. So I just want you to understand there are two types of friction. And so we're going to have to deal with them separately. So here's how we're going to deal with them, okay? We're going to look at this idea that there is mu that has a value for starting called static friction, and then there's a mu for once the object is in motion. We'll call that kinetic mu. So then we'll have a different level of friction once it's moving. Okay, so we're going to need to use that idea when we're starting things and doing some examples. Okay, so this is the idea of what friction is. Friction is how can be influenced by the mu, how rough the surface is, and how much they interact. And so if you have more weight, you can cause the friction to go up. And if I want to show that really quick, you could tell by this idea that I have a block. These blocks are definitely different size. So this one has more weight in than this one does. Okay, so if I put this one down and I want to pull it across the friction, you can see just to get it to move, it takes a certain amount of friction. It is like way up closer to 1.7, and you can see it jump into kinetic. But then if I pull this one across, okay, since it's not pushing down as hard, it won't take as much friction to pull it across. So it's closer to like 0.5, 0.75, okay? So it doesn't take as much because it's not pushing down as hard. And so when you change that, you also change how much friction you get, so how putting them together. So these are the two things that change friction, and this is the formula for friction. So now I want to do a chart. You ready? Here we go. We're going to do a chart, and we want to see what happens every time we change the original force, okay, that's applied. We have this object. It has a mass of 51 kilograms, and 51 times 9.81 rounds off to 500.3. I want three numbers, so 500 is close enough to the weight of this box. We're going to push this box, but we're going to keep changing how much we push. We're going to push at first with 100 newtons. Then we're going to push with 200 newtons, then 300, then 400, then 500. So this is going to be basically, we're going to start at 100 newtons, then we're going to go to 200, then to 300, and so on and so forth. Okay? And we want to find out what happens. But you got to remember, to start the box moving, it's going to take so much friction. To then keep the box moving, it's going to take less friction. So this is the start, and this is to keep it moving, which will be less. So we need to really find out how much each amount of friction costs or will take away from our system. So the force of friction, we found out from the equation I just gave you. Force of friction is mu Fn. But I'm going to use a different mu, so I'm going to give you, first of all, the starting friction. And so we take basically 500, and we're going to multiply it by the mu of starting, 0.5, whoop, clear, 500 times 0.5 equals 250 newtons. So it's going to take 250 newtons just to start. Okay? Then we have the force of friction as we get moving, 500 times 0.45, and that's going to cost us 225 newtons. So 225 newtons to keep it going. So it takes a little bit less friction, force to keep it going once it's in motion. It just takes us more to start it. So what does that mean? That means that until I've passed this part right here, my object will not begin to move. Just like earlier when I was showing you this block and I was pulling on this block, and it wouldn't until I got to a certain force, then it wouldn't begin to move, okay? And so we know if we're doing this chart, we know that it is not going to slide. So the answer is no and no. It will not slide. Why? Because we haven't overcome 250 newtons. But if I go to 300, it's going to be actually start moving. So the answer is yes, it will begin to move. Yes, and yes. And depending on the direction, my applied force is to the right, so then it would say to the right, okay, but if I had done the applied force to the left, then it would be moving to the left and my friction would be to the right. But remember, friction always opposes your forces in your motion. Okay? So that's simple to do. You just have to look at your starting friction, and then the numbers that are above it, it will then begin to move only until you've passed that amount. Well, how much friction is available? Well, it depends on how much you're pulling. The block or the friction only applies an amount to keep you still. So if I'm pulling with 100, and it could give me 200, but it doesn't have to, it will only meet me with 100 newtons. And what will it do? Well, if it's 100 this way and it's 100 that way, I'll have no net force left over, because 100 minus 100. But if I start to push harder, but static is still stronger, I might be pushing with 200 newtons, but it's also going to push back with 200 newtons. So friction's always going to meet you, But since it's meeting you, you will not begin to move yet. Now what happens when I start yanking on this and we start pulling on this situation or pushing on this with 300 newtons now? So now we're really going strong. So we're putting 300 newtons. We finally get it to move. What happens? Well, the friction drops. And so the friction now drops to 225 newtons because now it's moving. And here it was at rest. Okay, and at rest. So that means 0 and that means 0. But now we're moving, but not everything is going into motion because it's still resisting us the whole time. So basically I have to subtract this force minus this one because they're in opposite directions. So 300 minus 225 is 75 newtons. Okay? And so then what happens when I start pushing with 400 newtons? Well, I'll still have a resistance because it begins to move, but the resistance goes down because it's now under kinetic resistance. And so it's going to go down to 300 minus 225. So the friction is still 225. It won't change once it's in motion. So 400 minus 225 is 175. And you can probably guess it'll be 275 as we go up. Okay? But now we're in motion. Okay? And so that's how you would figure out what's going on. You could even go as far as to figure out the acceleration if you wanted to. And if we wanted to figure out the acceleration, it's pretty simple. If you have no net forces, F net equals ma. To solve for a, you would just divide by the mass. Okay? But if F net is 0, a is 0 because it doesn't matter how big your mass is. Your acceleration would be 0 meters per second squared. Okay, and these would be newtons, but it doesn't have the word on. Be careful. This would also be 0 meters per second squared. But now to find the acceleration once it begins to move, well, if I keep pulling it at the same rate, then I would just divide by the mass. So 75, and my mass is 51, divided by 51. I would begin to accelerate at 1.47 meters per second squared. So remember, the net force, what's ever left over after the friction and the other force fights, that would be left over, okay? So that's what I want you to think about. And if you wanted to go on, it would be 175 divided by 51 is 3.43. And then 275 divided by 51 is 5.39. And those are meters per second squared. Okay? So I just wanted to show you this. And so here we go. Okay? We'll talk to more, but that is how you do that. Have a great day.